Hey everyone. So in this bonus video, we want to talk about infection systems. So what are infection systems? Something like this kind of stuff. And basically what we're talking about here is attributes. So we're not necessarily talking about geometry that is growing, but growing attributes. The advantage of that is that you can use that for all kinds of stuff, for example, as masks in your shaders, but also if you kind of use it to drive your Houdini networks, you can also use it to make something look as geometry is growing. Again, we're talking about attributes, so do not confuse it with differential growth or diffuse reactions or something like that. This is purely for attributes. So to understand what an infection system is, let's look at this graphic here. And the idea here is that you have a couple of points, and in this case they are connected with lines, but that's not absolutely necessary. It just makes it easier to understand the concept. So let's say we start with one single point that has an infection, so we always have to start somewhere. And then you calculate is the spreading of an attribute, for example, by looking from every single point to its neighbors. And this is the approach we will follow most of the time in this video. So for example, this guy looks into its surroundings and see if there's any infection already there. So this guy is not infected. This guy he's not connected with, so in this case he wouldn't check for this one, but he would check for this one. He's not infected, but oh, there's an infection, and what that means is now he gets infected. That's easy to understand for a single point. Now if you follow the same logic for all the points, and let's go back to the beginning, then the next frame will look like this, because every single of those points here around the original infection point found a neighbor, at least one, that is also infected. And if you follow that to the next frame, then of course you have more, and the whole thing is basically spreading, and you have something, that feels like an infection, something that is spreading outside. Now, how do we implement that in Houdini? Let's start with a simple way, and we just have a grid here. And let's start by defining a first infection by just painting an attribute. You can call it whatever you want. I call it infect for some reason. And then, I don't know, I just paint a couple of numbers here that are higher than 0 to show you where the infection already is. And then another one with just a point maybe. Okay, so we have a couple of starting infections, and the easiest way of kind of stealing attributes from somewhere else is an attribute transfer, because an attribute transfer works in a spatial kind of way. So we can actually take we can steal from ourselves, so to say, the infect attribute. And if we visualize this, there it is. So the cool thing about the attribute transfer is that we can define a distance threshold and a max sample count. The max sample count is basically how many points does a single point look into the source around him, basically. So if I increase that, you can see what basically happens by default is it just blurs the whole thing. And this is basically already what an infection is, really. It kind of, if there is an infection somewhere close to a point, then this point will be somehow affected by this attribute. Now this by itself, of course, is kind of boring because it's just a single frame. So if we want to accumulate this over time, of course, what we need is a solver so that we can increase this effect. So let's start with our painted infection outside, and we just steal our attribute transfer and put it into a solver. And we just take the previous frame and we steal from it at the same time. There you go. Then you can see what happens is it's basically a blur. But at the same time, we see already that it's kind of working, because you can see that the attribute infect is actually moving outwards. The problem is, due to the nature of the blur, during this process, the numbers are actually going down, as you can see here. Now, just because it's the first kind of simplified version of doing something like this, what we could do is we can make sure that it doesn't disappear, but it constantly adds a bit more on top of it. So, for example, what we could do with the point wranglers, we can say, okay, the infect number should always be multiplied by 1.1, which means it gets 10% higher every frame. Now, be careful whenever you change something in the solver to look at the result from outside. So we pin our viewport here and rewind and see what now happened. And as you can see, this is way more looking like an infection. Let's go quickly back and lower this maybe to 0.5. So it's only 5% increase per frame, which might still be too much. But here you can see the effect. Now, it's not very nice looking, but it's a good way to understand how this system actually works. By the way, the reason you saw before that at some point it disappeared, we don't see it anymore, is that the number just becomes too high. As you can see here, because we increase it by 5% every frame, the number at some point goes higher than 17,000 because it's constantly increasing. What we can put in here is, or maybe we can do this with a new Vex, and I'm sure there is a clamp node or something that does the same thing, but I'll do everything in Vex. So I say if the infection is higher than 1, then make sure that the infection is 1, which basically just means it's a clamp to 1. It can never go higher than 1, as you can see here now in the geometry spreadsheet. This is really all there is, and my idea behind doing this way, even though it's actually not a good way of doing it, is to only use the nodes we already know and hopefully make it easier to understand what's actually happening here. Let's make this whole thing a bit nicer, because this is really not how you would do it. The way you would do it is usually you would write your own Vex code for this. At least this gives you the best results. And we will basically now write what we talked about on the slide before and really do this in form of Vex. So what we can use here is a very nice function in Vex called neighbor, or neighbors actually, neighbors, and that gives us all the neighbors around a point. And this allows us to kind of access all the data of surrounding points. So the way the neighbors function works, when we look into the help, is that it gets a geometry, which is 0 of course, and the current point number. And then it gives back an array of integers, so a list of integers. The way you write that is that you create an integer array, and then the name of the array, let's call it neighbor list or n list. And then at the end, you do those two brackets that define this is not just a single integer, but a list of integers. And then, of course, like we saw, it's a 0 and ptnum to read all the neighbors out. And when we run this, now in the nList variable are all the neighbors of each point. Now, to make this visible and easier to understand, let's actually expose this information to an attribute. And this is a bit different, because to create an array attribute, you start with a data type and then you use those same brackets before the at, which looks a bit weird, but it's the same logic. So let's call this nList as well and fill this attribute with the variable nList. And we should now be able to see in our geometry spreadsheet all the neighbors for each point in an array. There you go. Now you might wonder, okay, what does it find actually with neighbors? Now neighbors is a bit special because it finds everything that is directly connected. So in this case with the grid, let's say, so this point here has 4 neighbors, this guy, this guy, this guy, this guy. And this could be a way of, spreading the variable. We will look at different ways later on, but let's start this way. So what do we do with this? So first of all, we have to run through this, through every single neighbor point and check if he has an infection. And we can do this either with a for loop or with a for each loop. So I don't want to go too deep into this. Maybe you can do your own research into for and for each, and some of you probably already know this concept. Now with for each, it allows me to temporarily save something into it. Each neighbor that I'm looking at right now, I'm running over every neighbor, and then the current one is in temp, and the array I'm running over is called nList, and this is the syntax for that. And now I can use the integer, which of course describes the point number of the neighbor, to read out the infection. So I can do this with a point command. So I want from the current geometry read out the infect attribute of point, which point? Well, the current point that I'm looking at in my list of neighbors. So again, what we're doing here is we're reading out for each point all their neighbors, and then we run with for each over each of those neighbors and check if there is an infect, or read out currently the infection, and we save that into the infect variable. Now this by itself doesn't do anything because we haven't done anything with it yet. The next is we have to actually check, okay, if the infect variable of my current neighbor is higher than 0, then do something. For example, set my own infection to 1. And now something happens. And as you can see, right away on the first frame, something happens. And if I still have my viewport pinned to the outside, so if I run this now, I can see the effect, and you can see there's an infection. Now, this is even less nice than what we saw before, and the reason is it currently only knows infected or not infected, which is a bit boring because usually an attribute is, more complex than 1 or 0, and we can actually implement this into our system. So a better way to do this is to say, okay, if there is an infection near me, I'm not getting completely infected, but just a little bit. So we can say, first of all, that my infection should not be 1, but maybe I should add to my infection a little bit, like, 0.1. And then you can see that it grows still very fast, but the edges at least are a bit softer. Now, the same logic applies to what we're actually checking for. Currently, we're just checking if there's any infection at all. That kind of controls how quickly this is actually happening. So we could also say, okay, if there's a little bit of an infection, my infection will not increase. But it only happens if there's a lot of infection. So we could just increase this threshold. Currently it's 0, but we could increase this threshold to 0.5, let's say. And if you run this now, you can see the whole behavior is quite different. And this is really already what you have to understand. It's always the same logic. It's just that if you tweak the threshold, if you tweak the amount, if you tweak maybe some random factor into it, you can change the overall behavior. And this is actually where, it can become an endless pit of complexity because you can add all kinds of complexities to it. Let's, for example, lower the infection rate and not so much the threshold. And actually, let's put both into parameters. So the infection rate is one parameter, and then the infection threshold, let's call it, is another one. And now I can play around with those numbers. This defines how much it increases every step if it finds an infection in its neighborhood that is higher than the infection threshold, which we put to 0.7, let's say. Let's see how this behaves. And you can see it's much slower. So what will we change? Let's change the infection rate to speed the whole thing up to 0.5, let's say. And now you can see it spreads quickly, more quickly. So basically this is how an infection works, but it's a bit boring, right? And first of all, before we move on, be careful again. Let's look at our actual infect numbers. And again, they go up quite a lot because we have our infection rate here. So let's not forget to put our limiter in that we had before. So if the infection is higher than 1, then the infection will be 1. And this puts a limiter to how high an infection can be. And seeing that, let's actually lower the infection rate a little bit. And then you can see it looks like this. And let's call this limit. Okay, now this is all nice, but it looks a bit boring still. So let's make this a bit more interesting. There are many ways you can do to improve this. The first thing, and the order is not in a particular way, is that I would not work with those grid-like systems. With an infection system, it's always a good idea to have something a bit more crazy. And the best thing to do here is using a scatter. So I turn off the relax iterations and use a density scale and just use points for the whole thing. Now, if we just copy this, what we will see is that it doesn't actually work anymore if you run this. And the reason is that we used here a neighbors function. And the neighbors function works with, connected points, which we don't have anymore. As an alternative to neighbors, there's actually another one called near points. And the near points, as the name suggests, and it breaks now because it has more parameters, the near points works by distance, not by connected points. And if we look in here, the first thing is it uses point not as a point number, but actually a vector, which means it's based on the position. So let's use the position now. And what's also left is max distance and max points. Now we can only use max distance, but I always include max points, and I explain in a second why. So the max distance just means, okay, now that we don't base it on a connection, we base it on a distance and say, okay, how far do we look around our current point to find neighbors? I put this on a parameter and I call it dist, I think. And this is totally fine. This by itself will work. Let's increase it a little bit to maybe 0.1. And if I run this, you will see that our system now works. And it already looks better because you can see here the edge is a bit more interesting because it's not based on a grid-like structure anymore, but more on, a more chaotic underlying scattered points source. I will include the max points though, because this is kind of a safety net. Because if you have a lot of points, it basically says, okay, how many points should I maximum find? And if your distance is too high and you have a lot of points, then you could potentially find millions of neighbors for each point, and then your calculation time will explode. So I will always integrate the max points as a safety to say, okay, for each point, never find more than, let's say, 20 neighbors, and the rest you ignore. Otherwise, it will be just too calculation heavy. Currently it wouldn't matter really because we don't have that many points, but just keep that in mind. So nothing really has changed. Now, on top of this, I would actually, because it still looks boring, now add a very important functionality, and that is sensitivity or threshold or whatever you want to call it. So a way of defining, okay, how willing is a point to be infected? And to understand that, just imagine a piece of wood. Not everywhere the infection would happen in the same speed or in the same amount. You have maybe a dry area on the wood and maybe a wet area, and the wet area will be much more willing to be infected by a fungus. So we integrate this by adding another attribute, and I add this after the scatter with an attribute noise, and I call this sensitivity. Then the word doesn't really matter, but I found that sensitivity is a good word to describe what I want to show here. So let's visualize that. Oh yeah, there you go, because I have to look through it. And currently it's funny colors because it's a vector. So let's turn this into a float, and now you can see the idea. This describes, again, how willing a point will be to be infected. So to integrate this into our setup, you can actually, if you want, integrate this with the infection threshold, so multiply it by that. But in my experience, it works best if you multiply that with the infection rate. So here I just multiply it with sensitivity. Be really careful that you spell it right, otherwise the whole system will return 0 here, and then the whole thing doesn't work anymore. So now let's change our visualization back to infect, and let's see if we actually find a difference. Currently we can't see much difference, and the reason for that is probably that the numbers are not, different enough. So the best way of making this clearer is, in my experience, to use a remap simply to create more contrast on the sensitivity. Let's go back to the visualization of the sensitivity, and let's use the attribute remap sensitivity to increase the contrast. There you go. So now there are areas that are very unwilling to be infected or very slow in their infection rate. So let's watch this again. This time actually I will turn off I will not jump back and forth between the visualizations, but will quickly create two visualization nodes here. One for infect. There you go, and I visualize it with the ramped attribute. And the other one will be sensitivity. There you go. And now I can switch between the two and can see much better what's going on. So let's rewind. And remember, we increased the contrast of our sensitivity. And if we look at the result now, we should see that. And yeah, you can see it. There are some areas where basically the infection doesn't hold. And you can maybe see from the shape that it feels much more like a fungus now. Because that's how it works. The fungus will not expand in the same speed everywhere, but based on randomness or noise, you can control how quickly each point will be infected. Now we can play around with this. For example, we could lower the size of our noise with the element size. So here we go, maybe this, and we could also play around with the remap, and maybe then it looks something like this. Yeah, and this I think is not too bad. So just for fun, let's change the colors a little bit to make it a bit more interesting. Maybe if there's no infection, our visualization will be giving back 0. Highest infection is maybe a yellow, and from there it goes over a brownish, and then it would look something like this. Yeah, and you can of course control the speed of the whole thing with our parameters here. So you have your distance that it looks around, you have the max points. If you increase that, it will be faster. The threshold you can lower, and also the overall infection rate you can increase, and then the whole thing should be much faster. Play around with those parameters and how they influence the behavior. What you can definitely do, because you will potentially not change anything inside here anymore, I usually expose those parameters to the outside, to the solver itself. So I kind of make everything invisible that I don't care about, and then expose the parameters from the inside to the outside. And this way I don't have to constantly go in. And now here I have the control I want. So great, there you go. Okay, great. So now that we have this working for a grid, we can of course apply this setup to anything else as well. So we can, for example, let's do it for a single sphere, maybe make it a bit bigger, give it a lot more frequency, and maybe a mountain node to make it more interesting. Yeah, something like that maybe. And now we can just basically follow our logic here and paint the start infection. So with an attribute paint, we make sure that we paint an infect attribute. Oops, with C. I don't know, let's start a little bit of here, a little bit there, maybe here, and there's a little bit of an infection. And we can just copy the rest, because the rest is fine for anything really. So we scatter on the surface so that we have points instead of the geometry. Then we have our sensitivity noise. There you go. And now if we run this, of course, the same works on a geometry as well. And now you have it in 3D, which, could be, again, a fungus infection or something on a rock. I don't know. Now, what we can do with that, depends on you. A quick example would be to say, okay, we use this attribute for another scatter. So we transfer the attribute from the points back to our actual geometry. So the attribute we're transferring, of course, is the infect that we just saw. And we now use that. Oh, I think I used the wrong sphere. This one, okay. And now we use the attribute infect for our scatter. So our density attribute is now called infect. Of course, you could rename this too or whatever. And by adjusting the density, you can see now that the points will be scattered there where the infection exists. And if I rewind this and run this, you can see that we can now basically use this to scatter points. And of course, when we use that to copy objects to it, and for now spheres are fine, we can actually use the infect attribute as a p-scale. So we say our p-scale is the infection, which is pretty big though. So we can just make the sphere smaller, or we multiply the whole thing with a multiplier. I just make the sphere smaller. And if I turn this into something yellowish, maybe something like this, and I merge this with my rock, you can see this now looks as if there is geometry spreading over my rock. Of course, you could also do this to drive your shaders. There are all kinds of things you can do with it. And this is the power of using attributes instead of anything else, because with attributes, you're then free to use the attributes for whatever you want, including scattering objects like here. And here's a flipbook of that. And here is a render of it that, you know, it's adjusted with a couple of things like random scale of the spheres and a bit more random colors on the fungus. So feel free to experiment with the options of making this look nicer. This is just the core idea, and you can use that for all kinds of stuff. Of course, for other stuff than fungus as well. Okay, so this is Vex-based infection. I hope this was helpful. Thanks very much and see you later. Cheers.